Hey everybody, today we're going to work through the area of some figures that you should be pretty familiar with. The formulas aren't going to be too scary early on, and then we'll get into the times where it's a little bit tougher. So we're going to start with something that you've dealt with a trillion times, the area of a triangle, which is going to be 1/2 base times height. All right, now that's a formula you've heard a trillion times. When you are working through it, the most common thing that people do is they forget to do half of their figure. And that just comes from the simple fact that if you were to take a rectangle and then you were to chop it in half right down the middle, then it would create two triangles. So that's why we only want half of that area. That's why we do 1/2 base times height. So over here, you do 6 times 11, which would be 66, but then you want half of that number because, again, we don't want an entire rectangle. We just want half of that, and you get 33. Now, in this particular case, they didn't really give you a unit, but I do want to make sure we understand that, like when we're talking about an area, we're talking about square feet or square inches or things like that. So usually, whatever unit it is, you are going to have to include units squared. Now, in this particular case, I didn't give you a unit, so if you just want to put U, that works for me. Now, one of the things that are going to happen as we go is we are going to end up with times where they're going to give you information that you don't need, and you are going to have to sort out what to use and what not to use. In this particular case, the base is 90, the height is 60. That 78 over there is completely meaningless. And they're going to do that to you on end of course exams. They're going to do it to you on multiple choice tests. It's not going to go away. Now, in this case, you can get a calculator. Be comfortable with using a calculator. If you don't want to deal with 1/2, use 0.5. It doesn't really matter. Either way, you're going to get an area of 2,700 square units, which we're just going to say units squared instead. All right. Now, as far as the area of a parallelogram goes, you sort of know that with a rectangle, it's base times height or length times width or whatever you want to call it. It doesn't really matter. When it comes to a parallelogram, you can use that same sort of idea. And the reason why is because if we really wanted to, we could take a piece just like this. I'm going to take this piece. If you took that green piece and you picked it up and you moved it to the other side, you would end up getting, let's get rid of this and I'll show you what I mean. You would end up getting just a regular rectangle. So whenever we talk about the area of a parallelogram, so many times I see kids that want to use all the information, break it up into pieces, that sort of thing. The reality is the area of a parallelogram is just base times height. Or, if you want to call it length times width, it doesn't really matter. I like base times height better in this case because with base times height, you kind of differentiate the idea that, well, the 12 is important, the 13 isn't. All right, speaking of, if you're going to go through that problem and you're going to do the area of the whole thing, you're going to do 20 times 12. The base is 20, the height is 12. Ignore the 13, it's not important, and you get 240 units squared. Last but not least, in this picture right here, you've got a 10 and a 15 and an 8.5. What in the world are we going to do to figure out the area? Well, here's the problem. You need a base, you need a height. We don't have a height. So if we're going to go through and we're going to try to figure out the area of this thing, it won't work because we don't have that height. So instead, we have to sort of turn the tables. We have to rotate this thing around and give ourselves a mental idea of what's going on. So instead, what we're going to do is we're going to look at it from this perspective instead. What if we changed our perspective and we made 15 the base instead? So you can turn your paper to the side. You can do whatever you want. But essentially what we're going to do to get this problem right is instead of using the normal perspective, we're going to turn it to where the 15 is the base. And if the 15 is the base, then 8.5 is going to be the height. And then if you do 15 times 8.5, you would get 127.5 units squared. Okay. Now that doesn't seem like it's too bad. When does it get complicated? Well, sometimes they don't give you enough information. You know, it says find the area. So this next example, we've got ourselves a triangle. It's a standard triangle, and the area of a triangle is 1/2 base times height. The problem is we are given the base. We are not given the height. So we're going to have to go through, we're going to have to find the height. And since it is a right angle, we are going to do the Pythagorean Theorem. So to do that, we are going to set it up. We're going to say 12 squared plus b squared equals 15 squared. Now, when you do the Pythagorean Theorem, a and b can be in either order, but the hypotenuse has to be c. So that's why we put the 15 on the right side. Now, if we subtract 144 from each side, then we're going to get b squared equals 81. What number squared is 81? Sounds like 9 to me. Now, it seems like a lot of work, but it worked out really nicely, so we can just plug that in where it needs to go. So that means 12 times 9 is 108. Half of 108 is 54. And again, we're just going to go with units squared. We're not going to attach anything here. We're just going to go from there. All right. Now let's try this next one. Same idea. We've got a triangle, and we're doing area equals 1/2 base times height. The base is 8, but we need to figure out the height. Well, it looks to me like we're going to have to knock this thing in half. So if we were to split that in half, then that would turn this into a 4 and this into a 4. And the reason we did that, now what we have created is 2 right triangles, which means that same trick that we can use for the first example with the Pythagorean theorem, we can now use for the second one as well. So that's what we're going to do. 4 squared plus b squared equals 8 squared. Now, the one thing you're going to notice as you get through this problem, and it's going to be a little bit more annoying than the other one, 48 is not a perfect square, which means we're going to have to kind of break down that 48 into a couple of different pieces. So again, we want to know what b is. So you try to do the square root of both sides to figure out what the square root of 48 is. It doesn't work because 48 is not a perfect square. However, I do know that 48 is 16 times 3, and I do know that the square root of 16 is 4. Now, that's something we have practiced in previous chapters a whole lot. Hopefully, it's something that you still remember. If you don't, it's something you'll get better at as we go. But long story short, you've got 4 radical 3 for the height. Now, you will see 2 different types of scenarios. Sometimes you will be told to leave your answer in simplest radical form. If that's the case, then you can just stop and say, well, half of 8 is 4. 4 times 4 is 16. So you would write 16 radical 3 units squared. That is a very common way of writing things, and if that's what they ask you to do, you need to go with it. If, on the other hand, you want to, you could also just take the whole thing and just throw the whole thing in your calculator all at once. And that would be if it said estimate, or if it said round your answer to the nearest tenth, then you would throw it all in there and you would end up getting 27.71 units squared. Either one. Those are both correct answers. It really is just a matter of how you want to name it. So again, you've got simplest radical form, and you've got rounded to 2 decimal places. You need to just be aware of what they're looking for. All right, last example in this section right here, you've got a parallelogram, which we should know by now. The area is just base times height. So if you're just doing base times height, you could just break out a little Pythagorean theorem here, because whenever we're doing the height of a figure, it is straight up, which means it makes a right angle to the ground. So we could do more of the same thing. 9 squared plus b squared equals 41 squared. And it looks like it's just going to be a disaster. Huge numbers. What in the world is going on? Why do we have to do this? Well, turns out you subtract 81 from both sides and you just get b squared equals 1600. What number squared is 1600? It turns out it's a perfect square. Turns out it's 40. So all that work, and you find out the base is 60. Remember, you could just flip it either way. The base is 60. So if the top is 60, that means the bottom is as well. And then the height is 40. So it turns out we've got it. 2,400 units squared. Now again, if this said 60 centimeters, and if this said 40 centimeters, then the area would be 2,400 centimeters squared. So it doesn't really matter. Just use whatever language they are using. If they use centimeters, call it centimeters squared. If they use inches, call it inches squared. It doesn't really matter. Just go with it. All right. Now the last thing I want to do is do a demonstration of scale factor here. And I do think it's valuable because you're going to notice something really interesting about how area works. Okay. Now, in order to do this, I want you to draw this particular triangle. And the directions tell you what to do. You are supposed to put point A there, you're supposed to put point B there, and C right there. The area of ABC would be, well, you already know that it's going to be 1/2 base times height. The base is just from A to B going straight across. That is a base of 4. And then the height, if you go straight up and count the squares, 4 again. So 1/2 of 4 times 4. So half of 16 is 8. Now, what if you did a dilation with a scale factor of 3? So now instead of point A being at -2, -2, now it's going to be at -6, -6. We are tripling each number in the ordered pair. And that's something we did in the last chapter when we talked about transformations. So we are taking -2, -2, and we're turning it into -6, -6, and so on. We are taking every single ordered pair and we are multiplying every value by 3. Now what you're going to find now, the base isn't 4 anymore, it is now 12. The base is 3 times longer, which makes sense because everything should be 3 times bigger. Okay. The height is now 12. So the new area, if we do 1/2 base times height, is going to be 1/2 of 12 times 12. So instead of the original example, which was 1/2 of 4 times 4, now for our new one, the area is going to be 1/2 of 12 times 12. And half of 144 is 72. So we have now actually gone from 8 units squared to 72 units squared, which is way more than 3 times bigger. So the ratio of the new area to the old area is 72 to 8, which is actually 9. So if the scale factor is 3, the area is actually going to turn out to be 9 times bigger. Now, in order for you to see the pattern, I want you to try it one more time with one more triangle, and then we'll wrap up. So again, now you've got 0, 3, 3, 0, and 0, 0. As it is, the area is base of 3, height of 3. 1/2 base times height is 4.5. Now, if you did a dilation with a scale factor of 2, 0, 0 is going to stay 0, 0. There's nothing special there. But your other points, instead of 0, 3, it's going to be 0, 6. Instead of 3, 0, it's going to be 6, 0. So your new area, remember the old one was just 1/2 of base times height. The new one is going to be 1/2 6 times 6. Half of 36 is 18. The ratio of 18 to 4.5. So if you were to do, and you could do this on a calculator actually, if you did 18 divided by 4.5, you would find out that the area of the new figure is actually 4 times bigger. So essentially, when we're trying to figure out what area does to a figure, the area is not based on scale factor. The area changes based on scale factor squared. So when you're deciding, well, this thing is dilated with a scale factor of 3, that means the area is actually going to be 9 times bigger. If it's dilated with a scale factor of 2, it's going to be 4 times bigger. It's not based on scale factor, it's based on scale factor squared. Okay, so that's the last thing I want you to pick up as we go through this area lesson. All right, I hope this helps you figure it out. Thanks for watching. I'll see you next time.